This is the decision to sample paper. Let's just do it. We've got a recurrence relation question to start with, so if we rearrange this to be this minus this equals 0, this would be our auxiliary equation. You might recognize this as the quadratic that has has solutions that are the golden ratio. And of course, if you've got two real solutions, which is what this is, then un equals a times the first solution to the power n plus b with the second solution to the power n, where a and b are some constants to be found. So we have this, we're given this and this, so when u1 equals 1, so when you replace n with 1 here, these becomes 1s and this whole thing becomes a 1, and we get this. Of course, the 1s don't matter, you can times everything by 2 and you get this. When you replace the n's with 2s, this becomes a 1 as well, and you get this. You can 2 squared is 4 times everything by 4, you get this, which maybe leads to this. This is not the easiest simultaneous equation to solve, but thankfully you can just put it in the calculator and you'll get your answers pretty quickly. I divided that by 2, I guess, sure. And eventually the particular solution will be this with our a's and b's put in there. Now with the question done. Okay, excellent. So question number 4 then, question number 2 is one of the northwest transportation problems. So first we'll just allocate some stuff. So we'll put all 25 that are available from A into D. That leaves 13 left that D still needs. So we'll put 13 of these 55 there to help them, so that maxes out our 38 here. I should probably say 38 here to say that I've totaled it, but I didn't bother, which probably loses a mark. So just write 38 here to say you've totaled it. And then next, we just move along horizontally along the line. So, well, B has quite a lot to offer. E only needs 24, so we'll just put all 24 in there. And I think B still has 18 left over, it can still go up, and that makes this total 55. Again, this total is 24, I probably should have written, but I realised I've forgotten. It doesn't matter. 18 plus 18 makes 38. Sorry, no, 18 plus 20. This is the cost, of course. 18 plus the 20 that C can give makes the 38, and we'll be done with this. And again, put all the totals here. And then we can say the cost will be 25 times the cost for that route, which is 15, plus 13 times the cost of that route, plus 24 times the current, and so on, and we get this here. And now we're going to need to use the algorithm to make this better. So what I did was, most of the time you see these written as x's, I just write them as red in the numbers, because that way I only need to look at this table rather than this one. But we'll get the shadow costs out. Start with a 0 here. 0 plus 15 makes 15, so 15 goes there. What plus 11 makes 15, well that'll be a minus 4. What plus minus 4 makes 18, that'll be a 22. So we just want the shadows to add up essentially to make what's in here. So this will be a 14, because 14 plus minus 4 is 10. And then of course we need a 4 over here to make those two things add up. And now to fill in the rest of these boxes here, what we need to say what is this number, take away this one, take away this one. So 11, take 15 as minus 4, take 4 as minus 8. 12, take 22 as minus 10, take 4 as minus 14, and so on for these two. So 19, take 22, take 0, and then 9, take 14, take 0. Just remember this very algorithmically, and I think you'll be fine. The most negative is this one here. So what we'll do is we'll take this table here, and we'll put as much as we can in this box here. So let's put a theta in first. Of course, if you add theta to here, you can take theta away from here because you don't need, you only need 24 in total to go to E. So if you've got theta in here, 24 minus theta plus theta is 24. But of course, the same happens for the rows, right? You've only got 20 to take from depot C, whatever this is. So if there's theta here, this needs to be 20 minus theta. And likewise here, there needs to be a plus theta. It needs to be this 18 plus theta. And now I think the rows and the columns both all cancel out, so these two numbers can just stay as we had them before. And what we want to do is we want to make, we can't make any of these negative because we can't transport like a negative amount of things. So let's just make theta the biggest we can to keep everything positive, and that'll be making theta 20. That'll make CF the exiting cell, and that'll make CE the entering cell with these numbers here. So I've just replaced all those thetas with 20s, and I got these numbers here. Those are the exiting and entering cells, which they always want you to write down. And this will be our next stage. We can do exactly the same thing again to see whether this is optimal or not. So exactly the same thing. I put these numbers, the ones that I'm actually using, I put those in red. I'm going to do my shadow costs starting with 0. It ends up looking much like this. It's very similar to what we just did. And then of course we fill in these boxes doing the same method. So 11, take 15, take minus 10. Just be a bit careful. And then same thing all the others. We still have a negative. In fact, we've got 2 of them. This is the most negative, so we'll add in a theta to this box here, which means going back to this thing, that means theta needs to be taken away from this one to balance that out. it needs to be added in, I think, sorry, it also needs to be taken away from this one to make that row balance out, which means it then needs to be added into this one to make this column balance out. Now I think everything up and down is balanced and across. So we have this, the biggest we can make theta is 25, I believe. So we'll make theta 25, that'll give us this solution, just changing those for 25s, I think that makes that. And the exiting cell was this one here, was this one here AD, and the entering cell was AF, so just jot that down. And then, is this optimal? So we'll just do it one more time. We'll put in the costs for the boxes that we're actually using. We'll do the shadows, which look like this. So we start with 0 up here every time, then go to 9, which makes this a 1, which makes this a 10, and so on. And then we'll fill in the other ones, so this will be 15 minus 10 minus 0 for this one here, and then I've done them in a different order, 19, take 2, and so on. These are all positive, so this is an optimal solution. All the improvement indices is the particular term. A positive, they're not negative, so this is the optimal solution. And the cost, does it even tell me to work out the cost? I think I did, I don't know whether it actually tells me. But the cost is 38 times 11 plus 4 times 18 plus 20 times 12, and so on, and you get this number. And that will be question 2 done. Well worth learning the algorithm because, you know, it's a lot of marks to lose if you don't know it. So probably worth knowing the algorithm. We have some workers here, so this is going to be the Hungarian algorithm question. So we have some workers here. The first thing to say is if you're trying to find a maximum, Hungarian algorithms find minimums. So to find a maximum, we essentially just need to turn over all of these numbers. So what we do is we take the biggest number in here, which is 37, and we do every single number in this thing minused from 37. So 37 take 32 is 5, 37 take 32 is 5, take 33 is 4. So we're going to take 37 and minus all these numbers. And essentially what that does, because you've sort of almost flipped the problem over, is maximizing this is equivalent to minimizing this. And the Hungarian algorithm minimizes, so that's what we'll do from here. So we'll reduce the rows first. The smallest number in this row is 2, so take 2 from all of that row. Take 0 from all of this row, take 1 from all of that row, take 1 from all of that row. Then we'll do columns, so take 0 from this column, take 2 from this column everywhere, take 0, take 0. And now this looks pretty easy to cover up using 3 lines. Solution for a 4x4 table will be optimal if you have to use 4 lines. So this is not optimal. So what we'll do is we'll look for the smallest uncovered number, which is a 1. We'll take 1 away from all of the uncovered numbers, and we'll add 1 to the double covered numbers, which will give me this table here, I think. Yours may look slightly different because you can use a different arrangement of lines to do this, but that's fine. So I've taken 1 away from these 6 numbers, I've left these numbers alone except for these 2, which I've added 1 to. And that gives me this. I think that takes 4 lines to cover no matter how you do it, so it's definitely optimal. And all we have to say is, who does what? Well, the only person who can do R optimally is D, so D will do R. The only person who can do S optimally. Oh, where'd you go next? The only person. Everything has a. Oh, sorry. Now that you've chosen D to do R, the only person who can do P optimally is C. So we'll choose that. Now that C can't do this, A must choose S, and then B must choose Q, and that will be our choice. And yeah, I think. Did I ever work out how much that is? I would say at this point you should probably just work out what that is. So do D as R is 36. So do 36 plus 35, and so I'll just write that down. I don't actually know why I had to do that, but just write down the total that it would actually take, and that would be the answer. You formulate the problem as a linear programming method, so essentially what we're saying here is, like, we want to just put a 1 to denote who's doing which job and a 0 elsewhere, so this is kind of the table that tells you who's doing what. This tells you C is doing job P because there's a 1 here, and the others aren't doing it, and B is doing job Q, and so on. And so this is what this says. Xij is 1, this 0 should really be over here, but PowerPoint messed that up. I'm blaming PowerPoint, it was totally my mistake. Anyway, some entry, XAP say, is 0 if the person isn't doing the job, and is 1 if they are doing the job. So that's what this is saying, so that's what this table is getting out from. But also we've got some constraints, which is you can only put 1 in each row and each column. So we'll just write that as well. We'll say that the sum of this entire column, the P column, is 1. Because there can't be 2 1s there, and there also has to be a 1. So the sum of the P column is 1, the sum of the Q column, the sum of the B row, those are all 1s. We also obviously need to frame this to say we want to minimize the actual work done. So we want to minimize 5 times whatever we've entered into here, so 5 times XAP, plus 5 times xaq plus 4 times, and so on. So we want to minimize all of those added together, where most of these things are just 0, right? As I've said, most of them are just 0. But we want to minimize it anyway, and then we're also working to the constraints that the sum of the p column has to be 0, the sum of the a row this is, so the sum of any xa entry with any j's here, that has to be 1, because there's only allowed to be 1, 1, and there has to be 1. So sum of all the rows and all the columns is 1, and that's all that we have to write. Again, probably something that's just worth knowing how to do, because it seems like it comes up most of the time. Question 4 then is about cards. It's the decision tree question. So we start with a rectangle, and we have a choice here, so that's what the rectangle says. We can either play, in which case something will happen, or we can not play, in which case we get a payout of 0, because if you don't play, nothing happens. This -5 should turn up a bit later, but it's apparently just sitting there chilling, which is fine, I guess. Not annoyed about that at all. Anyway, when you choose to play, a couple of things can happen. Either you pick a 2, 3, 4, 5, or 6, which happens 5/13ths of the time, because there's 5 of those and there are 13 types of card. If that happens, you get plus 10 tokens. The reason you get plus 10 is because it costs 5 to play. So when you win 15, you're actually only winning 10 above what you had before. Now, if you lose, which happens 8/13ths of the time, because you don't pick a 2 or a 6, you have another choice to make, which is you can either keep playing, in which case we'll decide what happens after that, or you can not play. You can just sort of cash out and say, I'll take the -5 hits. You've paid -5 to get here, and you're just going to walk away with nothing else, so you lose this -5. If you choose to play again, then the rules are slightly different. If you pick either an ace or a king, which of course will happen 2/3 of the time, you'll win 40, but that's actually only winning 30, because you have to pay another 5 to do this again. So you're paying the 5 you paid to do this, and then another 5 here means you win 30. 11/13ths of the time, when you don't get an ace or a king, you're going to lose both of those 2 sets of 5. You're going to lose 10 coins. And this will be the entire tree now. So what we can do is we work out the value of this circle by doing 30 times this plus -10 times this, which will give us that. So that's the value here. Now that seems terrible, you're losing money, but at the same time here you're losing -5, and this is bigger than -5. You're losing less money by doing this. So the right choice is to play when you get to here. You're going to lose money, but you're losing less money than if you just walk away. And then we'll do it again. We'll do this times this plus this times this to give us the value of this circle, which is this, and this is greater than 0. So the correct choice is to play, in which case you're expected to win this number of tokens, which is about 1.48. And if you lose, or if you win, great. But even if you lose the first go, your optimal strategy is still to say, I'll play again. And that's just what we have to write to finish this off. Question 4 then, so the game theory question. So let's have a look at this. Why is one of the rows, why can you reduce this down? Well, if you look at the rows, this is obviously a question about dominating rows. I think it's this row and this row, if memory serves correctly. So B, if you see a negative number from B's point of view, that means they're winning money, and a positive number means B is losing money. So if we look at this column and this column, here B is winning 2, here B is losing 2, here B is winning 1, here is B is breaking even, here B is losing 2, here B is losing 3. So this, if he plays 4, no matter what A plays, he's going to win more or lose less by playing B. So we say, and you have to write this, that column 2 dominates column 4, and we can just get rid of column 4, because he'll just never play it. There's no reason to. Playing column 2 is always better. Find the play safe value, so we just find the lowest value in each row, and because that's the most they can be expected to lose, this is the most A could ever lose by playing number 1, which is more than the most they could ever lose by playing 2. So playing 2 or 3 is better from a safe value, because the most you're ever losing is 1, whereas here you could lose 2. Now for B, it's the exact opposite. You look for the biggest number, because again, these numbers are kind of opposite for B from B's point of view. This is losing 4, this is losing 3, this is winning 1. So the worst thing that can happen here is he loses 4. The worst thing here is loses 2, the worst thing here is losing 3. So the play safe strategy is to lose 2 and play this column here. Now, because the value of the play safe strategy for B, which is 2, doesn't match the value of the play safe value for A, which is -1, that means there's no stable solution. Or no saddle point is the other thing they might talk about. Now we're going to format this as a linear programming problem, P is equal to V. Now firstly, if you're going to program something into a game theory question into linear programming, you can't have any negative numbers in the table. So we're going to add 2 to every number in the table to make this table. And now that we've done this, we can program this as a kind of simplex algorithm thing. So, okay, we've got P1 of playing A, P2 of playing option 2, and P3 of playing option 3. So, okay, if B plays 1, your expected winnings are 6 times the probability you played P1, because and then plus 5 times the probability you played P2, plus 1 times the probability you played P3. It's kind of like a decision tree that we just did, right? So we times the probabilities and add them together. So our expected winnings are less than or equal to that. The next one, of course, our expected winnings if B plays 2, we do the same thing. Of course, this one just goes away, so we get these. And of course, for 3, we get these here. Now, when we're putting into the simplex thing, we'd move those all to the other side, wouldn't we, and add in a slack, but we actually don't need to, because that's all we really had to write. And that's done. So now that we know the probabilities, what we can do is we can just substitute those probabilities into here. Now 6 times 0 is 0, plus 5 times this is 15 sevenths, plus 4 sevenths is 21 sevenths. Sorry, it's not, it's 19 sevenths, because 15 plus 4 is 19, you muppet. So now we've got 3 sevenths plus 12 sevenths is plus 16 sevenths will be 19 sevenths. It's when you do decision maths, you lose the ability to do actual maths, like after you've done enough of it. It's just like regular adding just becomes, yeah, anyway. So this is 0, 4 times 3 is 12, plus 2 times 4 is 8, so that makes 20. But notice how these v's are less than or equal to this. So v can't be 20 over 7, because then this inequality would be broken. If the payout was actually 20 over 7, this would be bigger than this is, because this is 19 over 7. So therefore v is 19 over 7. But of course, remember, we changed this entire problem by adding 2 to the everything. So the expected payout is 2 more than it should be. So we're going to take 2 away, and we'll end up with the answer of 5 sevenths to finish up, which I believe is correct. I hope it is anyway. Find the value of C1 and C2. So we're going to take the maximum values that cut left to right. So 3 plus 3 plus 5 plus 7 gives us a capacity of 21, or value of 21. And then here we're going to take 6. This one's going backwards. So what we do is we take away the minimum that could be going through it. So it's 6, take 3 plus 5 plus 8, and we get 19. And there, that's that question. Explain the flow through the network that must be at least 12 and at most 16. So if you look at the exit, maybe, I think I did the exit first if I remember correctly, the most that can be going into this sink is 16. So the maximum flow is therefore 16. You can't put more than 16 through the start, because then you just won't have anywhere to put it at the end. Likewise, at the beginning, 5 plus 3 plus 4 is 12. So the minimum that can be coming out of the source is 12, and therefore the minimum that can be in the question is 12. The minimum flow in total. Explain why these must all be at the lower capacities. Now look for these things here. It's only 1 mark, so they must be connected in some way. DG, AG, EG, and FG are all of these. Well, look at the maximal capacity coming out of those. It's 6. Look at the minimums of these. 1 plus 1 plus 1 plus 3 is 6. So even if all of these are at minimum, that's the maximum of the out that can go from where they're going to. So therefore, all of these must be at minimum. If you made one even slightly above, it would be over the maximum that G can take, or going through G can take. So you just have to put that kind of thing in words. Determine a maximum flow pattern. Now, I thought this was fairly tough, but they've given you a good hint to start with, which is you've got 1 here, 1 here, 1 here, 3 here, and 6 there. So that's essentially what we just answered, is that we know the flow is going through there. And now we can sort of work our way around from here. So this one here must be a 1, obviously to balance D. So that's fairly clear. Now, looking at this corner here, the maximum that can be coming out of this is, the minimum that can be going through that is 5, and the maximum coming out of this is 3. So therefore, I think this is the only way to set this up, because we have 5 plus 3, 3 plus 1 plus 1 is 5. If we go bigger here, we can't go bigger on any of these, as we've already discussed, and so I think that's pretty much that. The next bit I thought was the toughest bit to figure out here, but you've really got to look at B here. Now, the maximum outage that could be going through B is this 9. 4 plus 5 is 9. The minimum coming in, well, we've already got a 3 coming in here. And then we've got another 3 and another 3 here, which makes 9. So we must have 3 here, and 4 here, 5 here. Like we just must have that going on. We can now balance E by putting 3 down, because 3 plus 1 is 4. And now we've just got to finish the last row here by doing some balancing stuff. And if you put 7 through here, take away 3 is 4, so we'll have 4 through here. We've got to put 7 there, because notice how 4 is the minimum that could have gone through here. So if you make this a 6, you lose 3 and you get down to 3, and that's lower than the minimum. So there's 4 going through here, balance this to get a 9 here, and then of course 9 here, and this will be our maximum flow, which will be 15, because 6 plus 9 is 15, or because 5 plus 3 plus 7 is also 15. Explain why the maximum flow is equal to the minimum. Well, this was the point here that was really that was critical. The minimum flow that can be coming out of C is 7. This 3 plus 4. So SC must be at maximum, right? Because otherwise it just doesn't balance, right? If this is a 6, as I explained, you just can't get through C. So this must be a 7, but we kind of already decided these must be 5s and 3s, working backwards from where we were at from here. And so therefore these must be, this is the only way. Essentially this is just asking you that this is the only way of doing it. 5 plus 3 plus 7 is also 12, is 15, which is the same as 6 plus 9, and so therefore the minimum is equal to the maximum that you found before. You can't decrease this, and you can't decrease either of these either, as we saw before. Okay, so that's that, and then what it wants us to do is say, no D is blocked, so we can't use any of this anymore. So I've redrawn it, and I'm just going to avoid using this section. To maintain the maximum flow, the upper capacity of one arc is increased. Now, as soon as I looked at this, it seemed to me that BF is a massive choke point, because you've got 3 things going in and only 1 way out. Now, GT also does that, so I thought about if BF didn't work, going to GT next. But it turned out BF was a way of doing it. So what I did was I tuned the max of BF up to 100, just to make it more than enough to take anything. And then what I decided to do was I decided to, because I'm an idiot, make everything coming out of this as big as possible. So 7 coming out here, 5 coming out here, 7 as well. I mean, this has to be a 7 as discussed, because you need a 3 and a 4 here. But I tuned these up to the max. Now, this is a dumb thing to do, and I'll explain why in a second. But anyway, if you've got 7 coming up here, we'll put 3 maximum coming down here. And that means you've got 3 plus 3 plus 5, which is 11, is it? Yeah, 11 coming through B. So that's good, except it's not, right? Because the max going up this way is 4, so we'll put a 4 here. And then, of course, this adds this, and then takes away this to make 11, and that's too big for this one. So I went overboard, and it's clear that I went overboard, because I'm looking for a maximum flow of 15, but I've sent out of the source way more than 15. So I went back to the drawing board, and I was like, okay, well, if I'm looking for a max of 15, I should only be sending a max of 15 out of the source. So let's tone it down. Let's make this a 5 and a 3. Let's go for the minimums. We'll send 3 down here, and this sends B to 3 plus 3 plus 3 is 9. And this goes quite well, because 9 plus 4 is 13. If I just get rid of 4 going up there, I can make this a 9, and then keep that as 9, and this matches up to what it was before. So if I can just get a 6 in here, which I'm pretty sure I can do, actually, because it looks like I can just make everything else up here the same, pretty much, except I'm going to increase this to a 2. Ooh, hang on, I've increased that to a 2, which means this should have been a 2. I've typed this wrong, haven't I? Let's quickly fix it on the fly. So this should have been 5 plus 7 is 12, it's 15, so that all works. This needs to be a 3 to make this a 9, and then this plan works. So this, there's only 2 left here, so this should just be a 1. That's just a typo. 5 minus 3 is 2. Split it between these two, 1 and 1, so that should be a 1, which makes that a 1. 1 plus 1 plus 4 is 6, and then it works. That just needs to be a 1, so I've just typoed that down. Wrong, but we've still got a flow of 15 going into the sync T. So that seems to work well. And we can, yeah, if we maximize this, we only need it to go up to 9, but if you put it up to a maximum capacity of 100, I guess that will work as well. Cool. Question 7 then is the dynamic programming question, which is a great question, and you should definitely learn how to do this, because you get an absolute ton of marks for just doing a lot of the same thing over and over again. I'll firstly just define the stage as the month. Of course, this is dynamic programming, so we'll work from the end. So our first month will be A. The state is how many boats we'll have in storage at the end of the month. At the start of the month. The action will be how many boats we'll build that month, and the destination will be how many boats we put into storage for the next month. So if we start in May, now we need to have 4 boats built or in existence at the end of May, and we're not allowed, or we don't want to put any boats in storage at the end of May. Presumably we're just taking the summer holidays off. So okay, what could you do? Well, you could have 2 boats in storage at the start of May, and then you only need to build 2, and you'll put none in storage. Now, what's the cost of this? Well, Each boat costs 350 to put in storage, that's 700 to put 2 of them in, and doing any building work costs 1500. So it's just 700 plus 1500, and that'll give you a cost of this. Now, you could only have one boat in storage at the start of May, in which case you would have to build 3 boats and then put none in storage, because obviously it's the end. So then we'll say, okay, well, putting one in storage costs 350, building 3 boats also costs 1500, and so we have a cost of this. If you had 0 boats in storage, you'd have to build 4, none go in storage later. 0 boats in storage means you don't pay any storage costs. You do pay 1500 to build the boats, and you also have to hire additional space at 800. So it will cost this. And now these stars, I'll explain a little bit more when they become more relevant. But for now, let's just go to April. So in April, you could start April with 2 boats in storage. At max, you can only have 0, 1, or 2 boats in storage. It says there. If you start April with 2 boats in storage, you could only build 1 and then just put 0 in storage. You could build 2 and put 1 in storage, but let's just deal with this first. So if you have 2 in storage, that costs 700. If you build 1, that costs 1500. And you're putting 0 in storage, which means you'll then have to do this strategy in May, which costs 2300, because you put 0 in storage, which means you start here in May with 0 in storage, and that costs this. Alternatively, you could build 2 boats and put 1 in storage, because you only need 3, and you'll have 4 here. So you put 1 in storage. Now, building 2 boats, you've got 2 in storage here, so that's 700. Building 2 takes 1500. And then, because you've got 1 in storage, you take this value from May, which is 1850, to finish up the work. So we're finishing, this number here represents all the work going back to the start, or the end, really. We add those up, we get this. One final strategy would be to build 3 boats and put 2 in storage, which means building 3 boats, having 2 in storage is this, building 3 is this, and then having 2 at the start of May is this much to finish, and you get this. Now, the most optimum strategy of these 3, if you start with 2 boats in storage at the start of April, is this one. So we'll star this one, and we'll never use these 2 values again. For any previous month, if we finish March with 2 boats in storage, we'll do this option here to continue. And we don't need any of these values anymore, and we actually don't need any of these, except we do for a bit, because we need to finish off April. So we'll start this time April with 1 boat in storage. That means we could build 2 and leave none in storage. That's going to cost 350 because there's only 1 storage, plus 1500, plus whatever it costs to finish May with 0 in storage, which is this. So we get this. We could alternatively build 3 boats, leave 1 in storage, or build 4 boats, put 2 in storage. That will cost this much and this respectively. Remember to add in the extra amount if you build more than 3 boats, and just use, if you finish with 1 in storage, that costs this to finish up. If you finish with 2 in storage, that costs this to finish up. And again, we'll select the most optimum strategy of the 1 boat in April in storage strategy, which is this one here. And finally, if you enter April with 0 boats in storage, you could build 3 and leave none, or you could build 4 and leave 1, or you could build 5. You can build up to 5 boats a month and leave 2. That will cost this, this, and this respectively, and the most optimum strategy is this one here. So if you enter April with 0 boats in storage, you're going to want to do this thing from then on. Leave 0 in storage for May, and so on. Then we just keep working exactly the same idea. We do the same for March. Now, March is kind of like a choke point almost, because you need so many boats. So if you enter with 2 boats in storage, you have to build 4 to leave 0 in storage, or you could build 5 to leave 1 in storage, making these 2 costs. That one's the better one. Or you could enter March with 1 in storage, in which case you'd have to build 5, because you need 6 by the end of March. 0 get left in storage, that costs this much, and that's the optimal strategy because it's the only one. And then we go straight to February, because that's the only thing you can do in March. You can't have 0 in storage, because you can't build 6 boats in 1 month. So that's all we can do. February is the exact opposite, because you need so few boats. So we've got a few options to run through here. I'm not going to talk about this in great detail. What I will say is that March is still choke pointing it a little bit, because you have to enter March with either 2 or 1 boats in storage. So if you enter February with 2 boats, you can't build none, because then you'd have no boats in storage for March, which is not a situation you can do. So you have to build 1 boat here at least, even though it feels like you don't have to. And we end up with this. You can only put, as well, at most 2 boats in storage, so we can't build any more than this. If we entered with 1, you'd have these options, and they would cost these things. Again, keep selecting the best for each state. We keep going, we keep doing exactly the same thing. You can pause the video and go through it much slower if you want to. We finally get back to January. Now for January, again, is a slightly interesting one because you cannot have any boats in storage at the beginning of January, so this has to be 0, and we're actually almost done here because there can't be any 1s or 2s here. So 0, you could build 3 and leave none in storage, you could build 4 and leave 1, or 5 and leave 2. That'll cost this much. The cheapest thing to do in January is this. So the cost in total is 9,450, and that involves building 3 in January, and then we follow the track. Like we've left none in storage for February. Most efficient thing to do there was build 3 in February. That leaves 1 in storage for March, in which case we build 5 in March. That leaves 0 for April, in which case optimum strategy was to build 3 in April. And that leaves 0 for May, in which case the optimal strategy was to build 4. And that will be the answer. Thank you so much for watching, and I'll see you next time.